one is quick integration by parts. So the integral of a function, you can eventually work out one is u and one is dv by dx and uv dash and whatever it might be. And you can churn through all of that to eventually calculate what the integral is. So this is a shorthand way of doing the same thing that I learned as an undergraduate at the University of Edinburgh. Hence, I'm going to call this the University of Edinburgh way. It wasn't them that invented it. And the maths and physicists in the audience, and indeed anybody really, should be able to go off and prove that this is correct. So I'm just going to do it, and then you'll see roughly how it works. And then the next time someone gives you a big, massive integral to do, you might be able to see that you can use this method. So let's do something which we know the answer. Well, let's do something. Okay, so let's write down a wave function. Let's say we've got r cubed e to the minus r over some value a naught. So that's our wave function, and we want to integrate this over all radius. So we're going to integrate from r equals 0 to r equals infinity dr. Okay, so it looks simple enough, and you're probably all thinking, oh dear God, I'm going to have to figure out which one is which and do it multiple times, because I'm going to keep ending up with another integral. So I'm going to make a column now. I'm going to make two columns. I'm going to call one d by dr, and one the integral dr. Just sort of shorthands. So I'm going to choose one of the bits of my integral to differentiate and one of the bits of my integral to integrate. So in fact, I'm going to choose r cubed as the thing I want to differentiate, and e to the minus r over a naught as the thing that I'm going to integrate. So I want to choose something to differentiate, which eventually will die off to 0. And then my list here will stop, and then when we do the sum, you'll see why. So I'm going to choose r cubed as the thing I want to differentiate. So I differentiate first once, I get 3r squared, differentiate again, get 6r, differentiate again, 6, differentiate again, 0. And then I'm going to integrate this one up. First integral, I'm going to get e to the minus r over a naught minus a naught. Integrate it again, I'm going to get plus a naught squared e to the minus r over a naught. Integrate again, minus a naught cubed e to the minus r over a naught. Integrate again, plus a naught to the 4 e to the minus r over a naught. And that's as far as I need to go, because now we've got 0. So we have to match these up. So I want to match up the top one with this one with that one, this one with this one down here, and eventually 0 with this one, but it doesn't matter because I got it to 0. And then the final trick is I'm going to multiply these two together, r cubed and minus a naught e to the minus r. But that one's going to have a positive sign, this is going to have a negative, positive, negative, positive, all the way down, alternating. Okay, so this is just the kind of shorthand way of doing it, which means that my integral is now equal to this first term here, so it's going to be minus a naught r cubed e to the minus r over a naught. The second term, minus a naught squared, or minus 3a naught squared, r squared e to the minus r over a naught. The next term, minus 6a naught cubed r e to the minus r over a naught, and the final term, minus 6 a naught to the 4 e to the minus r over a naught, and I'm evaluating that from r equals 0 to r equals infinity. So essentially now I'm just about done, apart from putting in my limits. So I've managed to get this whole definite integral without a lot of faffing around with integration by parts. So the shorthand does all the hard work for me. It makes sure that all my u's and v's and v dashes and u dashes and whatever else is in the normal integration by parts are carried out correctly in the right order with the right sign. So one column where we take a bit of this and we just differentiate it. So I choose r cubed because I know eventually that will die off to 0. And another column where we integrate the exponentials, fairly easy to integrate. Do that multiple times. Then we just need to multiply them across, down like this. And the only other trick is to remember that this is plus, minus, plus, minus, plus, minus, plus, minus. So there we go. So let's actually do it. So for the first term, if I put r equals infinity, this exponential equals 0. So this first term equals 0 at r equals infinity. The next term equals 0 at r equals infinity. The next term equals 0. So I might have an infinity here, but I've got an e to the minus infinity over a naught, and that wins. That goes faster than r goes up. And here again equals 0. What about at the bottom? I have minus a naught r cubed, so if r equals 0, this equals 0. Here, this equals 0. I've got an r, this equals 0. So this one, in fact, that exponential will equal 1. So what am I left with? 0 for 0, 0, 0, 0, 0. So I've got 0 minus 0, 0, 0 minus 6a naught to the 4. So the integral equals 6a naught to the 4. So it's a very shorthand way of doing what looks like quite complicated integrals to begin with. So that's my quick integration by parts, the University of Edinburgh way. I imagine they didn't invent it, but that's where I learned it. And you can do this for any integral which has a sort of polynomial times a function. So it doesn't work for sine times cosine, then you might have to work out something else. But it does work for any polynomial type of function, and most of the wave functions we're going to play with in this section of the course are a polynomial times a function. So therefore you can use this quick integration by parts to do something like, for example, you might want to add up the square of the wave function and show that the total probability equals 1, or something like that. In this case, it equals 6a naught to the 4. So then that would become your normalization factor. Okay.